In this video, I want to highlight two theorems for symmetric matrices, which concludes with the fundamental theorem for symmetric matrices. We saw in a previous video, and this is taken from 2 pages from the textbook we use for Math 2260, entry-level linear algebra. In that textbook, we have this theorem 7.9 is a property of symmetric matrices. When you have a square symmetric matrix and you have lambda 1 and lambda 2 being different eigenvalues of A, then the corresponding eigenvectors x1 and x2 are orthogonal. And as you look at the proof, it's the same proof that I showed you in the previous video. However, this is done in the context of the normal, usual dot product for Rn. Okay? So you have lambda 1 and lambda 2 are different, distinct eigenvalues of A, having eigenvectors x1 and x2. Alright, so you look at the dot product of x1 and x2, where you look at it as matrix multiplication, where x1 is a row vector and x2 is a column vector. So denote that by transpose of x1 times x2. So now you can write lambda 1 times dot product of x1 and x2, follow the equalities, put lambda 1 inside, then you have ax1, and then you take the transpose and put it over on the other side because A is symmetric, A is equal to its transpose. Follow it down to lambda 2 times x1 dot x2, and then subtract the ends and set it equal to 0. So that means that the product, lambda 1 minus lambda 2, multiplied by the dot product of the two vectors, is 0. But since lambda 1 is not equal to lambda 2, it follows immediately that the dot product of x1 and x2 must be 0. Again, that's because we have a positive definite scalar product. And then there's an example of eigenvectors of a symmetric matrix A, 3, 1, 1, 3. Show that any two eigenvectors of this 2 by 2 matrix are orthogonal, perpendicular. You see the characteristic polynomial is the determinant, lambda I minus A, and it turns out to be lambda minus 2 times lambda minus 4. You go through the process and you find the basis for each eigenspace. The solution space for lambda 1 is S negative S. The solution space for lambda 2 is T comma T. Okay. So when you take their dot product, you get 0. Notice how they did that there. Instead of using particular values for the parameters S and T, they just kept the parameters and took the dot product. And they get ST minus ST equals 0. That's a slick way to do it. So you conclude that x1 and x2 are indeed orthogonal or perpendicular. Finally is the main theorem, the fundamental theorem for symmetric matrices. Orthogonal diagonalization. A matrix A is orthogonally diagonalizable if there exists an orthogonal matrix P, or unitary matrix P, so that P inverse AP equals D, diagonal matrix. Now, P is an orthogonal matrix. That means what? it means that the inverse of P is equal to the transpose of P. Okay? So the theorem says, let A be a square matrix, then A is orthogonally diagonalizable, and it has real eigenvalues, if and only if A is symmetric. Alright, the proof in one direction is fairly straightforward, so let us assume that A is orthogonally diagonalizable. Then that means that there exists an orthogonal matrix, or we call it unitary in our book, a unitary matrix P, or we call it U, such that D equals P inverse AP. It's a diagonal matrix. Moreover, remember now, the inverse of P equals the transpose of P, or the inverse of U is the transpose of U, so that you get A is equal to PD P inverse, which is PD P transpose. Take the transpose on both sides of that equation, and you ultimately wind up with A transpose equal A, which proves that A is symmetric. The proof in the other direction is a bit more involved, but is still doable. Let's look at it. But it's very important. It's very constructive. Assume that A is symmetric. Okay. If A has an eigenvalue lambda with a certain multiplicity k, there's a previous theorem that tells us that lambda has k linearly independent eigenvectors. Alright, so the eigenspace that corresponds to lambda, the dimension of that eigenspace is k, where k is the multiplicity of that eigenvalue. Through the Gram-Schmidt orthonormalization process, the GSOP process, you can see then that this set of k vectors can be used to form an orthonormal basis of eigenvectors for the eigenspace V lambda. This procedure is then repeated for every eigenvalue of A. Then if you take all of these eigenvectors together, put them together, the collection of all resulting eigenvectors is an orthogonal basis, but they're not yet orthonormal. So by Gram-Schmidt, we have them orthogonal. Finally, we normalize them by dividing every vector by their norm to get a collection of orthonormal eigenvectors. Finally, we let P, or U, be the matrix whose columns are these orthonormal vectors. Then we conclude that P inverse AP is diagonal, and it's equal to the diagonal D, where the entries on D consist of the eigenvalues of A, so that A is orthogonally diagonalizable. I'll make one more comment about diagonalization of matrices. A general square matrix A, not necessarily symmetric, is diagonalizable if and only if the sum of the dimensions of all the eigenspaces add up to be n. So you may not have n distinct eigenvalues, but the sum of the dimensions of their eigenspaces, for it to be diagonalizable, must add up to be n. That concludes our video.